Good day, students. Welcome to mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 16 to 20 of the January 2019 Algebra 2 New York Regents exam. This will be a thorough coverage of the problems 16 to 20. If you need a much quicker consideration, look at the descriptions for the link to the high-speed coverage of this material. Don't forget to subscribe to our channel for updates to the remainder of this review series, okay? Alright, let's take a look at question 16. Question 16 is assessing our ability to generate functions or recursive definition for arithmetic sequences. Question 16 reads, Savanah just got contact lenses. Her doctor said she can wear them 2 hours the first day and can then increase the length of time by 30 minutes each day. If this pattern continues, which formula would not be appropriate to determine the length of time in either minutes or hours she could wear her contact lenses on the nth day? Okay, so in this particular problem, we are looking at an arithmetic sequence. How do we know that it's an arithmetic sequence? If you look at the growth pattern, it says it increases by 30 minutes each day. So if you increase by an amount, that's an additive relationship. So when you're adding a constant over and over again, that is an arithmetic sequence. Okay? Alright, so what we're going to do is we're going to generate the first 3 terms of the arithmetic sequence in minutes and hours, and then see which of these either functions or recursive definitions does not generate the 3 terms that we found. Okay? Alright, so let's start with the minutes term first. So she started with 2 hours the first day. Okay, so if she started with 2 hours the first day, that means the first term, A1, is going to be 2 hours, or in minutes, we know we have 60 seconds. 60 minutes in an hour, so 2 hours is equivalent to 120 minutes. Okay, so the first term for her sequence is going to be 2 hours or 120 minutes. The second term will be an increment by half an hour. Okay, so A2 is going to be 2 plus half an hour, which is 30 minutes or 0.5 hours. So 2 plus 0.5, which is 2.5 hours. Or if you want to write this in minutes, is going to be the previous term, which is 120 plus what? Plus 30. Okay, so that's going to be 150 minutes. Alright, so the first term is 2 hours or 120 minutes. The second term is 2.5 hours or 150 minutes. And then the third term in hours, do you see what it's going to be? In hours is going to be 2.5, the previous term plus 0.5. Write that correctly. 2.5 plus 0.5. And that will yield 3 hours. And how many minutes is 3 hours? 3 hours is 3 times 60, which is 180. Or we can just follow the pattern of the sequence and just add 30 minutes to 150 minutes. And we have 180 minutes. Okay? So the sequence under consideration here is in minutes is going to be squiggly 120, 150, 180, and the pattern goes on and on and on. Alright? If you want to write it in hours, it's going to be 2 hours, 2.5 increases by 0.5 hours every time, 3 hours, and then it goes on. Now, we have 4 combination of recursive recursive definitions and functions to generate these terms. And out of these options that we have right here, one of them will not work. Alright, so let's see which one works and which one doesn't. Let's start with option 1. So for option 1, A1 is 120. And this is a recursive definition. You get the next term by adding 30 to the previous term. Does not look like it's going to work here. Well, looks like it because this term grows by 30 minutes every single time. Okay, so let's generate the term. The first term, A1, is 120 for the minutes. That's a check. That's good. The second term, A2, is going to be the previous term, which is A1 plus 30. And then A1 is 120 plus 30, and that's 150. We have a match, check. And then A3, for A3, you take the previous term A2 and add 30. All right, so the previous term is 150, add 30, 180. Ladies and gentlemen, it looks like we have a winner here. Okay, this looks good. Well, we don't have a winner because we have 3 winners. So this looks good. Now let's move on to option 2. Remember, the question asks for which one that is not going to be appropriate. So we're looking for the one that fails. All right. For A2, we have a function. An is equal to 90 plus 30n. Let's test it out. So for the first term, A1 is simply going to be 90 plus 30 times 1. A1 is going to be, we're going to PEMDAS this, order of operations, 90 plus 30, which is 120. Check. Why do we have a check? Because that's the first term here, 120. We have a match. A2 is 90 plus 30 times the n. The n in this case is 2. Okay? Now if we work that out, we have 90 plus 60. 90 plus 60 is 150. Does that correspond to the second term? Yes, it does. Check. It looks like this one is good also. Let's try the third one. So A3 is going to be 90 plus 30 times 3 because n is 3 in this case. Using your order of operations, multiply first before you add or subtract. 90 plus 90 is 180. Check. Question 2 is good. All right, so question 1 is good, question 2 is good, which means they are not what we're looking for. Remember, we're searching for the one that does not work. All right, A3, option 3. Option 3, we have a recursive definition again. A1 is equal to 2. Now we're looking at hours, and the next term is defined by the previous term plus 0.5. Do you think this is going to work? Absolutely, because that is exactly what this sequence is, right? Well, let's look at it. So A1 is 2. That's the first term for the hours sequence. Check. A2 is the previous term A1 plus 0.5. The previous term is, what is it? 2 plus 0.5, which is 2.5. Are we surprised? No, because this recursive definition is exactly what this is. And then A3, what's A3 going to be? 2.5, the previous term, plus the growth factor, the common difference, 0.5. You get 3. And that's exactly what the third term is here. So we can clearly see that option 3 is a formula that will be appropriate for determining the nth term of any nth term here for this sequence that we have. All right, so since A3 works nicely, that means it's not the answer. Then our answer should be option 4 by elimination. Okay? All right, let's verify to make sure that it is correct. So for A4, we have a function again. So an is equal to 2.5 plus 0.5n. Okay, so the first term, let's test it out. A1 is going to be 2.5 plus 0.5 times 1. We're going to use the order of operations. Please excuse my dear Aunt Sally here. 2.5 plus 0.5. 2.5 plus 0.5 is 3.0. Is this the first term in any of these sequences that we have here? Most likely the arrow one. The answer is no. This is wrong. So since this is wrong, the first term is already wrong. That tells us that option 4 will not be appropriate to determine the length of time in hours for the nth day. All right, so the answer to question number 16 is option 4. So which one do you prefer? Do you prefer the function representation or recursive definition of arithmetic sequences? Let us know what you think. You can place your comments in the comment section below and let us know your preference and why you prefer that. All right, let's take a look at question 17. In question 17, we're going to be assessed on how to find the inverse of exponential functions. Okay? All right, so before we get started, let's go over the steps for finding inverses. Okay, so steps for finding inverses. It's just going to be a two-step process in this presentation. So what you want to do first, when it's presented in f of x notation, you're going to do a switch, okay? So remember, the inverse function does the reverse of what the original function does. So to reflect that reversal, we're going to do a switch, okay? We're going to switch x with the inverse of the output. The output, this is the output right here, okay? The output is f of x. So the inverse of the output is f inverse of x. So we're going to switch the in with the inverse of the output, and we're going to switch the output f of x with input, which is x. All right. After we carry out that switch, we are now going to proceed to solve for the inverse function f inverse of x, and we'll be done. Okay. All right. So another thing that you want to remember is a property of logarithm, the inverse property of logarithms. Okay. Inverse property of logs. There's just only one we're going to use here. Now, if you have log base b of b to the x, what's your answer going to be here? If the base of a log and the base of the exponent, that's the argument of your logarithmic function, if they are the same, guess what? They are inverses. They cancel each other out, and your final answer will be x. Okay? All right, so this is one of the inverse properties of logarithm. So let's go ahead and take a look at this problem. We have the function f of x is equal to a to the x. Now we want to find the inverse, okay? The function that does the opposite of what this function does. So now what we're going to do is we're going to take the output and replace it with the input. F of x becomes x. A to the, now the input x becomes the inverse of the output. So instead of x, we're going to replace it with f to the negative 1 minus x, like that. Okay, now what we're going to do is proceed to solve for this f to the negative 1 of x. Okay, so f inverse of x is an exponent. So how do we power it down? What legal operation can we execute to bring this power down? Well, since we have an exponent base a, all we just simply have to do is use the inverse of exponent base a. The inverse of exponent base a is log base a. So what we're going to do is take the log base a of both sides of the equation. So log base a of x is equal to log base a of what? Log base a of a to the f inverse of x. Okay? All right. So what happens here? On the right side, notice how it's similar to this property that we have illustrated here. If the base of the exponent and the base of the logarithm are identical, we have an inverse operation happening. So this and this a are inverses and take each other out. So we are left with log base a of x equals f inverse of x, which is our goal. Okay, we solve for f inverse of x. So using the reflexive property of equality, we can just write this as f inverse of x equals log base a of x. The answer to question number 17 is option number 3. Okay, so this is basically how you find the inverse of exponential functions. Now, how would you rate the level of difficulty of this problem on a scale from 1 to 10, 1 being extremely easy and 10 being extremely difficult? How would you rate the level of difficulty of this problem? Go ahead and place your rating in the comment section below and let us know why you gave this problem the rating that you gave it. Alrighty? All right, let's take a look at question number 18. In question number 18, we're going to be looking at how to generate exponential models. We're going to be looking at the compound interest growth functions for scenarios where the growth is continuous and a scenario where the growth is discrete. Okay? Question 18 reads, Kelly Ann has $20,000 to invest. She puts half of the money into an account that grows at an annual rate of 0.9% compounded monthly. At the same time, she puts the other half of the money into an account that grows continuously at an annual rate of 0.8%. Question: which function represents the value of Kelly Ann's investment after t years? And we have four options here. All right, so we're going to be looking at two exponential growth formulas to help us with this process. The first one will be the discrete one, where the interest is compounded monthly. All right, that will be the discrete, and the other one will be continuously. All right, so let's look at the two formulas separately, and then we're going to unite them together to solve this problem. All right, so the formulas that we're looking for, these are the formulas for compound interest. There are two of them. The first one is discrete, which is where we have n times per year, n times per period. Okay, n times per year or period. This is known as the discrete model. And for this one, the amount is going to be, well, let's use the f of t notation to be consistent with what we have here. F of t is going to be the initial amount, a1 plus, that's plus a1 times a1 times parenthesis 1 plus the rate in decimal form over n raised to the nt. Alrighty? Okay, how about the continuous one? The continuous model, what does that look like? For the continuous model, we have f of t equals the initial amount a1 times e raised to the nt. Bam. All right? So that's what we have. In Kelly Ann's scenario, we are looking at a combination. She's using the best of both worlds. She's using the discrete and the continuous. All right, so her function f of t is going to be a combination of both. All right, it's going to be a1 plus, times 1 plus r over n raised to the nt. This is the one that is compounded monthly at 0.9% plus the other one is going to be a1 e to the nt. Okay? Now for both of them, what we're going to do is we're going to oh, real quick correction. So I made a mistake with my formula. So it's RT, not N. So this is supposed to be R, and that's supposed to be R. Okay, so A1 e to the RT, and this right here is A1 e to the RT. Alright, so let's go ahead and write down all the knowns and unknowns for both scenarios, and then we just plug it in and then see what the final answer is. Okay? Alright, so for the one that's monthly, in this particular case, what's the initial amount? She started with 20,000 and she split it in half. Okay, so the first half goes here. So you know what? We can call this A1 for the first one, and then we can just call this A2 for the second one. Alright, so for the first account, her starting amount was half of 20,000, which is 10,000. Okay, and then the rate R is what is it? 0.9%. 0.9%. Ladies and gentlemen, this is a trap right here. You must convert your percent to decimal. Even though this is a decimal, it's still a percent. Okay, so to convert this percent of a decimal of in percent form into actual decimal, we will have to move our decimal point 2 places to the left. 1, 2. Very, very important. Let me put a star here. Whenever you're working with compound interest formulas, your percentages must be converted to decimal form. So the rate is going to be 0.009. Alrighty? And then n is the number of times per period, is monthly. How many months are there in a year? There are 12 months in a year. And then our t value is just t, since we're looking for our investments after t years. Okay, so with this information, we can formulate the first balance of the account of a first balance, which is a 10,000 investment in the discrete growth model. So we have 10,000 times 1 plus the interest rate in decimal form, 0.009, over the number of times a year, which is 12 months in a year, raised to the nt, which is 12t. Okay? Alright, now for the second account, we're going to add that on. She put the other 10,000, the other half, in here. Alright? So for this one, all we need is the rate. The rate is 0.8%. The time is just t, because we're looking for her balance after t years. So in this particular case, we're going to have A2, which is 10,000. E to the r, the rate is, should I put 0.8 here? 0.8, should I put it here? The answer is no. Remember, we talked about this earlier, that the percentage must be changed to decimal point form first. So 0.8% is 0.008. Now, how did that happen? It's just exactly what we did here. When you're changing from decimal to percent, your decimal point moves to the left 2 places. It's as though you're dividing by 100. Okay, that's what percent means. Divide by 100. So it's 0.008. So we're going to have 10,000 e to the RT, 0.008 t. Bam, like that. Alrighty. Now, if we take a look at just the second model that we have here, we can eliminate some distractors. We can eliminate 3 and 1, because if you look at the powers, this is 0.8 and this is 0.8. Those two are incorrect. So the correct one is going to be either option 2 or 4. Okay, so in order to figure out which one is correct, we will have to actually evaluate the quantity inside this parenthesis here. We are going to use our calculators to help us with that simplification. So it's 10,000 times, let's plug it into the calculator. So we have, let's clear that out, 1 plus 0.009 divided by 12. Okay, so it's 1.00075. Alright, so it's going to be 10,000 times 1.300075 raised to the 12t plus 10,000 e to the 0.008t. Ladies and gentlemen, can you see what the correct answer is? You can clearly see that the answer is option number 4. Okay? This is a combination of both discrete and continuous growth models. Alright, so let's see. Answer to number 18 is option number 4. This one, number 2 is wrong because of this piece right here. Now, question for you, which one do you prefer working with? Do you prefer working with the continuous or the discrete growth models? Let us know in the comment section below, and let us know why you prefer working with that over the other. Another thing to consider is which one do you think is faster? If you're trying to invest your money, which one do you think would yield you a higher balance quicker, the discrete or the continuous growth models? Let us know what you think about that question too, okay? All right, let's take a look at question 19. In question 19, we're looking at how to generate functions and equations given a factor and a graph. Okay? Question 19 reads, which graph represents a polynomial function that contains x squared plus 2x plus 1 as a factor? Okay? That is not the function. We're given a polynomial that contains this as a factor. So this is just a factor. We're given a factor and not the entire polynomial function. So keep that in mind, all right? Okay, so if this is a factor, then what should the related function look like? That's what we're trying to do here. So we have x squared plus 2x plus 1 as a factor, so we can easily use the factors to determine the roots or x-intercepts of the related quadratic function. Okay, so what we're just going to do is basically set this to 0. We're going to find the zeros of this quadratic equation, and it will tell us what the roots of the actual graph will look like. Okay, all right, so to do this, we're going to factor this real quick. So let's solve this. And we factor this, we will have, what will we have? AC, we're going to use the AC method here. Okay, so AC is just 1 and then B is 2. So you ask yourself, what two numbers multiply to give you 1 and add to give you 2? The answer is 1 and 1. 1 times 1 is 1, 1 plus 1 is 2. Now in this particular problem, A is equal to 1. The leading coefficient is 1. So in this particular case, we can skip the grouping process. We do not have to do any grouping. We can jump right to the factored state. That is simply going to be x plus 1, since we have a plus 1 here, and another x plus 1. Okay, equals 0. And what we'll do is set it equal to 0. So x plus 1 equals 0 and x plus 1 equals 0. If you solve both of them, you're going to have x equals to negative 1 with a multiplicity of 2. This, ladies and gentlemen, is known as a double root. Whenever you have a double root, visually, it just tells you that a vertex will be touching the x-axis at that particular value. Okay, so let me show you what I'm talking about. In option 1, we have a double root right here because the vertex is touching the x-axis right there. In option number 2, we also have a double root right here. Okay, so you can narrow down your options just based on that. Okay, so now that we know what double roots are, let's look at the graphs and see which one has a double root of negative 1. We're going to go at this blindly, okay? We're going to assume as though we don't know what this information is. So let's take a look at question 1. We have a double root here, and we have another root here. Let me change my color real quick. We have a double root here, and we have another root here. So what does that tell me? It tells me that the roots of this polynomial function is x equals negative 1. Because it's a double root, it's going to have a multiplicity of 2. And the other root is x equals 2. Okay, so do we have a match already? Absolutely. Look at this. Right here we have x equals negative 1 with a multiplicity of 2 as part of the solution, and we already have it manifesting itself here. So that automatically tells us that the correct answer is option 1. All right, but let me show you what this looks like as a function, as an equation. So the related equation is going to be as follows. If you have x equals -1 with a multiplicity of 2, that's simply going to be, you're going to have x plus 1 times x plus 1. Or you can write x plus 1 square, or x plus 1 times x plus 1. Okay? And then we have x equals 2 as another root, so that's going to be x minus 2 equals 0. So what we're doing is we're unsolving. All right? So if you look at this right here, this is the factored form, and we see that x plus 1 times x plus 1, which are factors of this expression, shows up here. So this piece right here is x squared plus 2x plus 1. All right, this is a factor of the original polynomial function. Now let's take a look at option 3. We're going to break that down also. All right, so for option 3, we're going to guesstimate a little bit, okay, because all the roots are not on lattice points. So we have one root here, which is -1. Perfect. And this one, let's just say it's in the center, okay, -1/2. And then this one is right between 1 and 2, so this one is 1.5 or 3/2. So this graph tells me that the roots are x equals -1, x equals -1/2, and then x equals 3/2. All right, so what are the related factors that generate these roots? We're going to unsolve this equation. So for the first one, we just add 1 to both sides. X plus 1, that equal to 0. And then this one, you multiply by 2 and add 1. So x plus 1 equals 0. And then this one, you multiply by 2 and subtract 3. 2x minus 3. So when you solve these three equations, you're going to end up with these three roots, okay? And then all we just do is multiply them by each other. And that will give us the polynomial function with this graph right here. So it's going to be x plus 1 times 2x plus 1 times 2x minus 3. And we see why this is not the answer, because we do not have any x plus 1 repeated in the complete factorization of this graph's function, okay? All right, now let's move on to option 2 and see what that looks like. For option 2, ladies and gentlemen, we have a double root again. Okay, so we have a double root here at 0. That's a double root. How do we know that it's a double root? Well, because we have a vertex touching the x-axis right there. Okay, so we have -1, we have double root at 0, and then 1, 2, 2. All right, so what do the roots look like? For option 2, the roots are going to be x equals -1, x equals 0. This one will have a multiplicity of 2, and then the other one will be x equals 2. All right, so in factored form is going to be, so add 1 to both sides, is going to be x plus 1, and then this has is already x equals 0 is already solved, but we're going to have it with a multiplicity of 2, so that's going to be x times x, and then the last one, you just minus 2 from both sides, and you will have x minus 2. Do you see why this is not the answer? We see that this is not the answer because x plus 1 does not show up twice in the complete factorization of the equation with this graph right here. Okay? Okay, let's take a look at option 4 and see why that is not the answer. So this is -1, 0, and 1. We have three roots here. So the roots are x equals -1, x equals 0, and x equals 1. There are no double roots here. So the related factored form is going to be x plus 1 times x, this one you minus 1 from both sides, equals 0. All right, and we can clearly see that this is not the answer also because x plus 1 does not show up twice. Correct answer for question number 19 is option number 1. So cancel 3, 2, and 4. Alright, so question for you to think about. Why do you think it's important to be able to find the roots both graphically and algebraically? So graphically and algebraically, why do you think it's important to be able to find the roots using both methods? Let us know what you think. Just put your answer in the comment section below. Tell us why you think it's important to know both methods, and then we'll see what you think. Alright, for question number 20, we're going to be taking a look at how to calculate the half-life amount given a table. Okay, question 20 reads, sodium iodide 131 used to treat certain medical conditions has a half-life of 1.8 hours. The table below shows the amount of sodium iodide 131 rounded to the nearest thousandths as the dose fades over time. So we're looking at radioactive decay here. Alright, question. What approximate amount of sodium iodide 131 will remain in the body after 18 hours? Okay, so what we need to remember here is the formula for half-life. Let's go ahead and write down what the formula is. Formula for half-life calculations. So the formula for half-life calculations is the final amount A is equal to A sub 0, the initial amount times 1 over 2, because we're dealing with half-life, raised to the time divided by the half-life. Bam. Okay, so in this particular problem, all we just need to know is the initial amount, the time, and the half-life. And we are good to go. Okay, let's specify what each components mean so that it's easy to follow. So A is the final amount. A sub 0 is the initial amount, what you started with. T is the time. And T sub 1/2 is your half-life. Okay, alright, so in this particular problem, we need to start by finding what A sub 0 is. A sub 0 is the initial amount. But if you look at this table, it tells us the amount after 1 hour. So it says number of half-life. So after the first half-life. So after the first half-life, there's 139. After the first halving. So can you figure out what the initial amount is? The answer is yes. If you divide something by 2 and you get 139, how do you undo that division by 2? To undo division by 2, you simply multiply by 2, right? Because the inverse of division is multiplication. So since the first halving results in 139, we're just going to take that and double it. Okay? So 139 times 2 will give us 278. So the initial amount was 278. 278. Alright, looking good. Now, the time, where it says how much sodium iodide 131 will there be after time of 18 hours? Was the half-life of sodium iodide, the half-life we're told is 1.8 hours. Okay, so 1.8. And then what's the amount? That's what we're looking for. Alright, so put everything into the formula. And we have A sub 0, 278 times 1 over 2 raised to the time, 18 divided by 1.8, the half-life. Okay, so you need to be careful about how you enter this into the calculator. One little mistake will totally ruin your result, alright? We want to make good use of parentheses here to communicate exponential terms and bases and coefficients with the calculator. Remember, our calculators are not mind readers, so we're going to make sure that we are precise. Okay, so we have 278 times 1 divided by 2. Put that 1/2 in the bracket. This is the base of an exponent. What is the exponent? The exponent is a quotient. So encapsulate that in its own parentheses. 18 divided by 1.8. so that there are no grouping errors in the calculator. All right, press enter. Press enter. 0.271 rounded to the third decimal place. All right, so the amount left is approximately 0.271. The answer to question number 20 is option number 3. All right, so a question for you that I would like to think about is, if you take a look at this model right here, how can you tell that this is a decay model? Can you or can you not tell? Let us know what you think. Post your response in the comment section below and tell us, if you just take a look at this model right here, can you tell if it's a decay model? Yes or no, and let us know why you selected the answers that you did. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is extremely important to us. Don't forget to subscribe to our channel for updates to the remainder of this review series. If you have any questions, comments, or special requests, feel free to post it in the comment section below and we'll be more than glad to respond. A lot more resources can be found at our website, mathgotserved.com, under New York Regents. Do check it out. Thanks again for watching and have a wonderful day. Goodbye.